Hello, everybody. I'm Rob Davis from NVIDIA. And first of all, I want to thank SNIA for inviting me to talk at the Computational Storage Summit. This talk is about combining GPUs and DPUs to make a neat off-the-shelf computational storage solution. All you need to add is your software. For some DPU background, I am guessing DPUs are maybe new to some of you. They are a new player in the data center. In this industry, we love acronyms, and DPU stands for Data Processing Unit. Like the GPU, which accelerates compute for the CPU, the DPU accelerates data movement for both the CPU and DPU. Data movement for storage in the case of this talk, of course. But more than that, it adds security to protect that storage from unauthorized access with little effect on performance because of its hardware offload engines for encryption and user isolation. Just a quick FYI, on many of my slides, I have links where you can find more information on what was covered in that slide if you want to research it further. DPUs are like little data centers on a chip. So what is inside that chip? It can vary from vendor to vendor, but in general, they all start with an SoC, system on a chip, another acronym, sorry. The NVIDIA DPU is based on an SoC ASIC called Bluefield. The major components are the ConnectX NIC for I/O, an ARM CPU, a PCI switch, and multiple hardware data accelerators. At a high level, these components are the same or similar inside most DPU vendors' products. The ConnectX RTL, this is not a chiplet design. It's a full-blown ASIC. So we're just taking that RTL, and it can do networking speeds from 10 to 400 gigabits per second on both Ethernet or InfiniBand. This is the same RTL that goes into our standalone NIC products. Next comes the CPU. With NVIDIA, it's a small multi-core ARM. It's a multi-core ARM, not necessarily small, with DDR5 memory interface, is more than one. And there is a next there's a 32-lane Gen 5 PCI switch, which provides connectivity to both the internal, for the internal functions. Last, offloading the ARM or host CPU from cycle-intensive or low-latency dependent functions. So for now, now that you know what's inside, you can see how they are able to offload, accelerate, and isolate all kinds of data center workloads. Some of those are listed here. But for this talk, I'm going to, of course, focus on computational storage workloads. In case this is your first talk at the summit, here is a quick introduction to computational storage. In my opinion, computational storage is often tightly connected to edge computing. So we're going to talk about that too. Another way to put it is edge computing is an area where computational storage makes a lot of sense. And here's why. In the data center compute function, you usually have CPUs and GPUs and their applications tightly connected to the storage through a high-performance network into which DPUs are now integrated. The application running on the CPU or the GPU asks for data through their storage interface, which sends a request through the network to the storage system. The storage system responds by sending the data, which is then worked on, and the results are saved back to the storage system, again through the network. Assuming a high-performance network and storage system, this all happens in a few milliseconds or less. But when we look at the edge computing model, There's no way for the data center application to be tightly connected to the data through a high-performance network. Instead, we have a wide area network connecting the stored data to the data center application. Maybe it's even just the internet. This means there is too much latency or delay in moving the data to the application on the compute in the data center. So we need to do something different. And that is called computational storage. Since we can't move the data to the compute, we are going to move the compute to the data. Sounds a little like something I learned in Sunday school, but I don't remember the details other than Muhammad was involved and a mountain. Anyway, we start out by separating the application into two parts. The part of the application that needs the data to make its calculations or decisions is moved close to the storage where the data is. The part of the application that needs the results of the calculations or needs to report on the decisions taken stays where it was in the data center. The calculations or computations move to the compute now on the edge, and the control stays in the data center. Of course, computational storage doesn't have to be tied to edge computing. If you have a slow or too busy network, it can be very useful in a data center as well. Let's look now at some computational storage solutions. The first one is based on FPGAs, field programmable gate arrays, more acronyms. These are chip devices that can be reprogrammed to different applications or functionality requirements after they are integrated into the solution's hardware. So they're very flexible that way. This is what makes them different from ASIC-based solutions, which are designed for a specific solution set or range of them, and tough to repurpose outside of that, although they can be pretty general in what they're designed for. FPGAs can be programmed for certain specific, much more specific computational storage applications by programming the compute or decision function for a specific application into them, and they run at the speed of hardware. The idea is when you have a new application, you just reprogram that FPGA. Unfortunately, this is great in theory, but isn't as easy as it sounds. FPGA programming requires a high level of technical expertise and training, which is often hard to find and the whole process is not done very quickly. They also usually need a CPU to control or host them and manage the reprogramming process. And you need to figure out how to locate them near, or inside the storage system. One place some vendors locate FPGAs is inside the SSDs themselves. This does get them pretty much as close to the storage as you can get, but they only have access to one SSD's storage, so it limits the scale of the solution. Instead of FPGAs, you can add more CPU power to the SSD to enable computational storage applications to run there, which of course means you need to add more DRAM too. Unfortunately, SSD form factors have power and cooling limit specifications, right? You can only, SSDs go into a certain size slot, they can use a certain amount of power, et cetera, et cetera. They're very tightly spec'd. And that really limits the computational storage applications you can put on them. But most important of all, the SSD vendors are volume companies. They ship hundreds of millions of units per year. The problem is the customers of 99% of those SSDs don't care about computational storage, nor do they want to pay for the extra added components needed to implement it. Of course, a CPU is a great computational storage solution option. It can be programmed easily and comes embedded in a server, which can have lots of storage, but it will be limited to computational storage solutions a CPU can handle. This leaves out the very fast growing market for AI at the edge and all the capabilities it can provide. Also, some computational storage applications require very large data sets, for example, video. Those and other edge AI data sets can be enormous. This can be a challenge for CPU computational storage solutions to consume and process that much data. This is the graph from my CEO Jensen's keynote on one of our past GTCs or GPU technical conferences. It is showing how companies have moved, customers have moved from processing gigabytes of data with CPUs to hundreds of terabytes of data with GPUs. This is what we see in the field. This brings us to what I think is the best computational storage option, and that is combining a GPU and a DPU together. The solution fits on a PCI adapter card. It is based on widely available from multiple vendor components, GPUs and DPUs, that are used in hundreds of other use cases. The DPUs and GPUs are designed for extremely high performance and programmable with well-known tool sets by commonly trained computer engineers. And DPUs provide very high performance connectivity to almost unlimited storage capacity through network or PCI connections. So here's how a computational storage based on a PCI adapter with DPUs and GPUs on it could be easily put together today. Start with a DPU-based JBOF, which are in the market today and gaining a lot of traction because of the many advantages they have over CPU designs. You can see this here. On the left is a typical JBOF, just a bunch of flash designed with an x86 CPU and its supporting memory, a PCI switch, and a couple of NICs and SSDs. These have been in the market since NVMe over Fabrics came out, 5 or more years ago. These general purpose CPUs are designed for ultra fast compute. It's just there to convert NVMe on PCI to NVMe over Fabrics on the network. It kind of seems crazy or much overkill and much unused CPU capability. On the right, you see a DPU implementation of a JBOF with the same functions. Remember, a DPU is designed to offload, accelerate, and secure data movement, which seems like a perfect fit. And you can easily see the advantages in power, cooling, real estate, and cost, which makes this approach very popular. Here is a design in the market today. For high availability, the maker uses takes two DPUs and dual port SSDs. And for flexibility, they use DPUs on PCR cards, which allows them to switch to PCI bus extenders for DAS solutions, but is perfect for what we need it for. By simply replacing the DPU PCI adapter with a GPU plus a DPU adapter, we can easily transform this existing JBOF product into a computational storage solution. Of course, we still need the software, but here is a solution which adds that. It removes the need for local data warehousing from a data search application with what they call an AI-enabled smart data lake. They use GPU plus DPU adapters and their AI software to search through documents, video, and other data types based on queries at GPU speeds. It works with documents scanned at remote sites and likewise stores video and other kinds of data sets. And it converts them to whatever format you want to look at them on the way out. Really cool application that runs on one of these computational storage, DPU plus GPU devices. And you can think about what other AI applications running on GPU on the GPUs next to all that stored data in this hardware solution could be trained to perform. I mean, think of facial recognition or shopping patterns or video abnormality detection or factory quality control, et cetera, et cetera. The list is endless. AI applications like the ones I just talked about and the one I showed, and others are often challenged by storage performance requirements that we talked about earlier about the CPU. This is not only because of the enormous size of the data sets that needs to be moved to the GPU for many applications, but also because of how fast GPUs can process the data they are given. If you compare the amount of time it takes for a CPU to process and perform its storage I/O cycle to that of a GPU, as we do in this chart, you can see the issue. If the I/O speed is the same, the GPU will be waiting for data to be loaded or the results of its calculations to be stored. That's because the I/O was designed for CPUs. In order to efficiently use the GPU, you must dramatically improve the storage I/O performance. A technology called GPUDIRECT storage does just that and is part of the capabilities of DPUs. Before GPUDIRECT storage, the network storage data path for GPUs worked like this. Storage data in the read direction is first moved from the SSD on the storage system to the memory of the SSD driver, then to the storage stack, then moved to the memory of the network stack. Then the network adapter sends it across the network where it moves to the network stack of the GPU's host CPU, which moves it to the host memory, where the AI application can now move it to GPU memory. Lots of memory moves and software getting in the way of performance. With GPUDIRECT storage, most of those data moves are eliminated, and the data is moved with the two network adapters RDMA hardware accelerators directly from the SSD driver memory in the storage system to the GPU memory across the network. This, of course, can increase the performance of the GPU's application dramatically in IOPS, bandwidth, latency, and reduces its host CPU utilization. But it does require using the RDMA-based storage protocols like NVMe over Fabric and NFS over RDMA, which DPUs, of course, support. RDMA, if you don't know, is the memory version of DMA, or direct memory access. This is a hardware engine in the CPU that moves data blocks from one memory location to another without software involvement. With RDMA, the hardware engine moving the data is in the NIC, and the memory locations are, of course, on both sides of the network. GDS also works with local NVMe SSDs across a PCI bus in the system hosting the GPU. Here, the data moves directly from the NVMe SSD to the GPU memory with DMA, bypassing the CPU memory and software stacks. So this would be how you would access data in the JBOF that was local, that we showed, the application I showed just before. I'm guessing you feel like you've just taken a drink from a fire hose with this talk, so I'll summarize with some key takeaways. First, GPU to DPU solutions are perfect for computational storage solutions, including AI. Second, they leverage common components, common system architectures, and common software and industry expertise. And third, GPU plus DPU solutions are enabling computational storage AI to seamlessly move to edge computing. Thank you.